Okay, so we're going to go through how to do celestial spheres. So, like we talked about on the notes, celestial spheres are going to show us what the path the sun takes on any latitude that you go to on Earth. So, a few things to think about when we're talking about latitude. We need to kind of remember that 90 degrees is the pole, the North Pole, and that the equator is going to be at 0 degrees latitude. So everything in between that, so if we're talking the Earth here, I'll just kind of draw a little demonstration of the Earth. If we have our North Pole up here, that's at 90 degrees. And then we have our equator, which is at 0 degrees. That makes a 90-degree angle. So they're 90 degrees away from each other when we're talking about the North Pole and the equator. So now thinking about a celestial sphere, that is, if you're standing in Olympia, then you would always be seeing the same stars as long as you stayed here. If you went somewhere else, you would see a different set of stars. So your dome around you is your two-dimensional set of stars that you see all around you. So I'm going to draw it two-dimensionally and three-dimensionally to help you guys kind of get an idea of what it looks like. So after I draw my dome, I erase any extra. So I'll usually make my line and then do my dome for that. Okay, so the next thing that I want to talk about is directions. So there are directions for the celestial sphere. We always put the north on the right side, the south on the left side, and the east in the middle. If we do it three-dimensionally, same thing goes, north, right, south on the left, east goes in the front, and west goes in the back. So this three-dimensional, I'm not very good at drawing them, is going to help for that situation. So I'm going to bring up, while we're in here, a PowerPoint of ours. Okay, so if you go back to the notes from the apparent motion notes, you will notice that on the fourth slide, we have this vocabulary. So this vocabulary is super important for what we're doing here with the celestial spheres. So each one of these are something we're going to label on our celestial sphere. The zenith, which is the point directly above the observer's head. The north celestial pole, which is going to be their latitude, and it's always going to be where the North Star is. So the North Celestial Pole actually means the point that comes directly out in the sky from wherever the pole is pointing. So if the North Pole is pointing at Polaris, and I talked to you guys about this before, Polaris is the North Star, whatever latitude you're at, that's how far the North Star is going to be above the horizon. Now the celestial equator is going to be 90 degrees away from that. So in the sky, the celestial equator is going to be straight up from our equator, but that means it's also 90 degrees away from the North Pole, just like we talked about the North Celestial Pole, just like how the North Pole and the equator on Earth are 90 degrees away from each other. The winter solstice technically means the sun is out very little. It's the shortest day of the year. But that's going to be a path the sun takes on the winter solstice and then the summer solstice. So you will want to follow through these. I'm not going to have both of these up when I'm showing you how to do these. I'm just going to be going through how to do them. But this is the equations you use, subtraction and addition only, but these are the equations you use to fill out your celestial sphere. So I'm going to go back to those celestial spheres. And the first thing on the vocab list was the zenith. So that is the point that is 90 degrees above the observer's head. That's going to be marked with a Z. And the second point that was on there on the vocabulary was the North Celestial Pole. So remember, the North Celestial Pole is going to be the part or the point where the North Pole would point. It's also going to be where you would see the North Star. So the NCP is what we abbreviate as the North Celestial Pole, the NCP. In this case, let's say that we're going to be doing 35 degrees latitude north. So we're always going to try to do the northern hemisphere, but I am going to show you what it would look like in the southern hemisphere, at least on the two-dimensional one. So just for sake of showing you, I'm going to draw the bottom half of the Earth. Now remember, we're in the northern hemisphere. Here's your little dome. You're looking up. But imagine what would happen on the bottom hemisphere, like if we were opposite. So remember, the seasons are always opposite in the southern hemisphere. So we're going to see what the sun's path would look like for the whole thing. Now, I'm not very good at doing it three-dimensionally, so I'm not going to do it on this one. I'll just do it on this one. Okay, so the NCP is always equal to the observer's latitude. That means the North Star is going to be 35 degrees above the horizon, and it's going to always be on the north side, okay, because it's the North Celestial Pole. So if we were to split this in half, 90 degrees would be from the zenith to the north side, and 90 degrees would be from the zenith to the south side, okay? So just kind of think of that. So if this is 90 degrees, I need to put my North Celestial Pole at 35. So we all know that half of 90 is 45. So below that, just below the half mark, is going to be about where 35 degrees is going to be. And we're going to label that the NCP. And just as a reminder, that's where the North Star is. So I'm going to do the same thing over here. Now, it doesn't have to be perfect. I know you could break out a protractor and we could get the angles perfect. But right now, we're just going to try to be as close as we can. And, that will be good enough. You don't have, if you put the NCP at 35 degrees way up here by 90, then that would be wrong. But if you're close in the vicinity, it'll be okay. So the next thing that we need to do is what we call our celestial equator. This one we have to solve for. So our celestial equator is going to be abbreviated as CE. Now remember, the North Celestial Pole and the celestial equator are 90 degrees away from each other. So if I move my pencil 90 degrees away from the NCP, I should be somewhere in this region over here at a 90-degree angle, okay? So how do I get that? How do I get the exact number? If it's 90 degrees away, we have to do 90 degrees minus that latitude or where the NCP is. They're both the same number at 35. So 90 minus 35 degrees is going to give us what our celestial equator is. Okay, so you can plug it into your calculator if you need to, or if you just kind of know how to do it off the top of your head. You're going to get 55 degrees, and that's going to be where your celestial equator is. Since it's 90 degrees away, it's going to be on the south side of your diagram. Okay, so again, to kind of make it accurate, you can make a 90-degree angle, or you can kind of just say, okay, I'm eyeballing it. It's a little bit above 45, since this is a little bit below 45. We're going to go at 55 degrees, and we're going to call that our celestial equator, which is CE. All right, since this is a path the sun takes, this is going to actually have a line drawn. The celestial equator is also the path the sun takes on the equinox. Remember, the equinox is fall and spring when there's equal day and equal night. That also means that the sun rises exactly east and sets exactly west. No matter where you are on this earth, the sun on the equinox will rise in the east and set exactly west. So that means the line for the path that we make has to go exactly to the east. So that on this diagram, I make my CE at 55 degrees. Since it's more three-dimensional, I'm not very great at drawing it, but I'll do my best. It's going to start in the east. It's going to come up and peak at 55, and then it's going to come down and set exactly west. So you can see that path a little bit better visually. The sun will rise, go across the sky. So you're here watching, right? And it's going to set exactly west. So the highest it will get in the sky at this latitude, as long as you're here at 35 degrees north, you're going to see it only reach 55 degrees, okay, in the sky. That's as high as it will get. Okay, so that is going to be our celestial equator. Now we need to do our winter solstice. That's what's next on the vocabulary. Our winter solstice is going to be our important day of where the shortest day of the year is. So we can assume that the winter solstice means the sun's going to be lower in the sky when it peaks. And it's also going to be out for a shorter period of time, meaning that the line is going to be shorter for the path. Well, this is where our magic number for the tilt comes in. That 23.5 degrees of the tilt, that's what makes the winter solstice, the celestial equator, and the summer solstice. That's what makes our seasons. So it gives us summer, fall, and spring, and then winter will be below it. So 23.5 degrees is the magic number. We need to take our celestial equator, that's this number we just found, 55, and subtract 23.5 degrees. So 55 minus 23.5, that's the tilt. That's going to give us where we put our winter solstice. So 55 minus 23 is going to equal 31.5 degrees. And that means that we need to put it in at 31 degrees. So if 45 is here, 31 is going to be a little bit below that. And we're going to call that our winter solstice at 31.5 degrees. So the key to this one is the winter solstice and the summer solstice, the paths always have to be parallel to the celestial equator. So if the celestial equator goes exactly east, the winter solstice line has to be parallel to that. And it's going to, and I'm going to darken it in a little bit. I have to adjust my arm. It's going to go parallel to the winter solstice. To the celestial equator. So these lines are parallel the whole time. Now, if I were to do it over here, again, they have to be parallel. So you can see the sun is going to rise in the southeast. It's going to peak at the 31 degrees. So that's as high as it will get on the winter solstice. And then it's going to set in the southwest. So it will barely be out for a very short amount of time. It's just going to rise and set pretty quickly. That's why we have a very short day. And then the last thing that's important to know is what we call our summer solstice. That's the longest day of the year. If we subtracted 23.5, we are going to add 23.5 degrees to 55 to get our summer solstice. So 55 plus 23.5 is going to give us 78.5 degrees. Now remember, this is 90 up here. Okay, so 78 is going to feel closer. Like some people get 100, the number 100 in their mind, and they think, oh, 78's got to be much smaller than that. But remember, this is 90. So we're only 11 degrees-ish away from the zenith. So if I were to do 78, and also note that if this is 23, this spacing here, the spacing between the winter solstice, the celestial equator and the summer solstice should be really close to that. So I'm going to put it about here because that's about where it looks like it's right. Might be a little bit higher if I were to break out the angles. Summer solstice is going to be at 78.5 degrees. Now remember, it has to be parallel to the celestial equator. So there we go. I'm going to draw it and I'll move my hand out of the way. So this distance here should be 23.5 and this distance here should also be 23.5. So they should be relatively the same when you eyeball them. Might not be perfect, but relatively the same. So that on this one would mean that the sun is going to go up, peak, and set. So right here, we're going to have the sun rise very northeast. But notice it still only crosses its peak in the south side. So it's going to rise. If you were to be looking, say you were looking off this direction towards the south, the sun would rise behind you in the east, so to the northeast. It will cross up into the southern sky, come across the southern sky, peak at 78.5, which is pretty high. And then it's going to set very northwest, so kind of behind you, because remember, you're looking off to the south. So it'll set kind of behind you on the west side. So that means that the path of the sun is much longer, hence the longest day of the year. And it's going to be higher in the sky, giving us more direct solar radiation. So it's going to be warmer. 35 degrees would be somewhere in the kind of middle Southern California area, if we were talking something you might be familiar with. So we know that it's warmer down there. The lower the latitude we go, the warmer it gets because it's closer to the equator. So why did I draw the southern hemisphere? Remember, everything is opposite. So I'm just going to take these lines and lightly sketch them all the way down. Whoops, that was not even. Try that one again. So if I sketch them all the way down through the southern hemisphere, notice what happens. It's exactly the opposite. So our summer solstice line, it's summer solstice here. Notice where it would be for them. So if I were to flip this over, this is the summer solstice line. Oops, I'll give you guys a better view here. Everything's upside down. There we go. So you can see it's our summer solstice line. It would be their winter solstice. Okay. And their celestial equator, it's going to be exactly the same. Remember, I told you, everybody, and look, it rises exactly east, just like ours does. Everybody has the same amount of daylight, 12 hours a day, 12 hours a night. Now, how high the sun gets changes. So as we go higher in latitude, these lines get lower. As we go lower in latitude, all these lines would move up and get higher. So the height the sun reaches changes based on latitude, but everyone still receives 12 hours a day and 12 hours a night on the equinox, and the sun will rise and set exactly east and west. And lastly, their winter solstice, our winter solstice is going to be when the sun is the highest, or their summer solstice. So everything's opposite that way. Now, three-dimensionally, you could do that as well. I'm terrible at drawing. Let me get my camera back going the right way. I'm terrible at drawing three-dimensional lines when it comes to these loops for the sun's path. So you can imagine, though, it would be the same deal. There would be more of a loop going through each of these. Okay? So couple rules to think about. Rule number one is that the celestial equator line always goes due east. So no matter what, you have to put the celestial equator line to the point that you marked as east, which is right in the center of the celestial sphere. So rule number two is the winter solstice and summer solstice are always parallel to the celestial equator. So these lines are always parallel to each other. And we know that this is 23.5 degrees, and this is also 23.5 degrees. If we were to add those together, it happens to equal 47 degrees. No matter where you go on Earth, that doesn't change. How high the lines are in the sky changes, or how low they are, but the distance between all of them means the sun will never go further distances than the total of our tilts together, 47 total degrees. When you add 23.5 plus 23.5, you get 47. So the sun will only cover throughout the whole year, no matter where you go, 47 degrees. So we're about to go into our winter solstice. That means we're going to hit this day here. And what's going to happen is it's going to be the shortest day of the year. The sun's going to rise and set really low. And then we're going to start moving back to the next season. So the next day, our sun's going to get a little higher and a little higher and a little higher until it hits good old spring. Once we get to the spring equinox, we're going to head to summer. It's going to get a little higher, a little higher, a little higher until we hit the summer solstice. And then we're on our way back down. We're going to head to fall. The sun's going to get a little lower and a little lower and a little lower until we get to the fall equinox. And then we're going to go back to winter. And it just does that all year round. The only thing that would change it would be if our tilt changed. If we got a more extreme tilt, this number would get further apart. If we got less of an extreme tilt, then these numbers would get closer together, the paths. That's why if we had no tilt, every day of the year would be like our spring and summer. We would have it rise in the east, set in the west, every single day. We'd have 12 hours a day and 12 hours a night, and we would never actually have seasons. It would be kind of fall and winter all year. Fall and spring all year round, at least at our latitude. You go down to the equator, it'd be summer like it always is all the time. Okay. All right. So I am going to do one more just to go through it with you. If you feel like you already get it, you can move on. But I want to do one where we go up a little higher past the Arctic Circle. So we're going to do one at 75 degrees north. And it's just a reminder, the Arctic Circle is at 66.5 degrees. And I remember telling you guys last Wednesday, that the Arctic Circle, that line means that if you go above it, there's going to be so many days that the sun does not rise, or if you go there in the summer, that the sun does not set. Okay, so just remember the Arctic Circle at 66.5 degrees. If we go above that, we have to look for the sun not setting or not rising on the solstices. So let's draw it out. So I'm going to draw my dome. Once I get that done, I always erase that extra on the end. North, south, east. If I want to do it three-dimensionally, north, south, east in front, west in the back. I'm going to label my zenith first. It's a point 90 degrees above my head. Okay. And I'm going to start with my north celestial pole. Since we're doing 75 degrees north, our north celestial pole is going to be at 75 degrees above the horizon. So on the north side, remember this is 90, half is 45, 75 is going to be up there. We did 78 earlier, so remember 75 will be up by the top. So our North Star, the higher we get, the North Star gets higher in the sky. Remember we talked about if we went to the North Pole, the North Star would be right above our head at 90 degrees. So we're close to the North Pole, not quite, so it's at 75. It's really high in the sky. That's our North Star. So here I could do the same thing. All right. Now we need our celestial equator. So I'm going to still, just for the sake of showing you guys the southern hemisphere, drawing my lower part, and then I'll write underneath of it, CE, celestial equator. So remember, to get the celestial equator, it's 90 degrees away from the north celestial pole. So it's on the south side, 90 degrees away. So it's going to be pretty low in the sky, which makes sense because the higher you get in latitude, the lower the sun's paths will get. That's, you have less sun up there, or you go up there, you know that it's cold. There's less direct sunlight. So the celestial equator is going to be 90 degrees minus our latitude we're at, which is 15 degrees. And that makes sense. I just showed you 90 degrees away is going to put it really low in the sky. So we're going to be down here at 15 degrees. That's going to be our CE, or our celestial equator. So remember, the celestial equator has to go exactly to the east. So that line I draw has to go exactly to the east. It kind of gives you this really shallow angle here. And if I were to do it on this one, going to barely touch the, oops, that's not a very good curve there, but it's going to barely peak at 15 degrees. And then it's going to set exactly west. So this is our celestial equator. This is our equinox days. So notice above the Arctic Circle, we're way up there. We're at the top of the Earth. The sun on the spring and fall equinox only gets 15 degrees above the horizon. That's so low, meaning even on the spring equinox and the autumn or fall equinox, the sun is only 2.5 fists above the horizon if you were to use that method. Very low. So we're going to do our winter solstice, and you might note that, okay, wait, if we use our celestial equator, that's 15 degrees, and we take away our tilt, that's 23.5 degrees, we're going to get a negative number. Well, remember, I told you, if you go above the Arctic Circle, some days the sun will not rise, and we are above the Arctic Circle, so on the winter solstice, it will not rise, and several days before it actually does rise, it will stay below the horizon. So if I do that, I get negative 8.5, and negative just means south when we're talking latitude lines. So I'm not going to put negative 8 here. I'm just going to put 8.5 and call that my winter solstice. Now remember, it has to be parallel to the celestial equator. So I'm going to continue my celestial equator line just like I did in the one above it to show you. So we know that the celestial equator line is going to always be the same, but show you what the winter solstice does. If it has to be parallel, that means it has to stay parallel the whole time. If it didn't rise, that means it stayed in the southern hemisphere the entire time. So if you were in the southern hemisphere, you would actually have daylight the entire time. It would never set. So we're going to go and do the summer solstice. We're going to take our celestial equator, 15 degrees, and add the 23.5 degrees. So we are now going to get 15 plus 23.5 and get to 38.5 degrees. So we're going to go up above the horizon. And remember, these are about the same distance. So I'm just going to kind of eyeball it and make it the same distance. Now, due to this angle, we've got such a low angle. All the paths are such a low angle. If the sun did not rise in the winter solstice, that means it's not going to set for the summer solstice. So if I do it right and draw it parallel enough, I should note that my sun will not get below the horizon here. So didn't set. It will be 24 hours of daylight on the summer solstice at 38.5 degrees. So it didn't rise here. It didn't set here. So anytime you go above the Arctic Circle, do remember the sun will not rise on the winter solstice and it will not set on the summer solstice. Now here it's really hard for me. So if I was going to do it three-dimensionally and I didn't want it to peak, you're going to kind of notice that your loops, your paths are going to look kind of funny. And then same here, if you wanted it to, if it's not rising, or I'm sorry, it's not setting, it's still going to reach kind of like this weird angle and come back down. So I'm terrible at the three-dimensional ones when it comes to being at the Arctic Circle because I do not do a good job with keeping those lines parallel. But two-dimensionally, you can see that. So what happened? Look at the difference between the two. Here we were at kind of a latitude that's lower, closer to the equator, kind of the California range. Notice that the sun's path was much higher. As we went up in latitude, so we're trekking towards the North Pole, all the paths tended to sort of shift downward. So they were up higher, and then as we went towards the equator, they're going to shift downward. So by the time we actually get to, I'm sorry, not the equator, the North Pole. By the time we actually get to the North Pole, they're going to keep shifting till they're like this, right? If we were to go to equator, go back down, California, Mexico, get to the equator, our lines are going to shift themselves this way, okay? So that's what's really important to kind of understand. And this is all due to the tilts and where you are and what your view is based on what latitude you're at. Okay, so if you're getting this, this should be pretty easy for you to do the worksheet. If you are not getting it, I'm going to do one more so you can keep on this if you'd like to. I'm going to do one that's at the tropics. So I'm going to go towards the Tropic of Cancer. And I'm actually going to go inside the tropic towards the equator to show you what the lines do. Most of the time, the lines always stay on the south side over here when we're talking where we're putting the lines for each of these. But once we get to the tropics, we will notice that we'll start seeing the lines kind of be on the north side a little bit. So I'm going to do one more, and I'm going to do it for just below the Tropic of Cancer. And we'll do it at 21 degrees north latitude. So I'm going to squeeze it in here because I don't have a lot of space, and I'm not going to do the three-dimensional one just for space, okay? So I'm going to put it here. Oops, break my pencil. And, oh my goodness gracious, keep breaking it. And I'm going to make my dome. I'm going to label it north, south, east. I'm going to label my zenith. All right, so at this point, remember you're standing on it. We've gone really far south. We're inside the Tropic of Cancer. We are somewhere tropical, and it's going to be nice and warm. So we can imagine that the sun's going to be much higher in the sky in all positions, winter, summer, spring, all of it. Okay, so since we're at 21, the North Celestial Pole is going to be down at 21. Remember, I told you as you got towards the equator, you would notice that the NCP gets lower and lower in the sky, the North Star, to where if we got to the equator, it'd be right on the horizon, so we wouldn't see it. So this is at 21 degrees. That's where our Polaris would be. So this is going to be 90 degrees away from it, the celestial equator. So if this is really low, we know our celestial equator will end up being pretty high in the sky. So I'm going to do it off to the side over here so I can make our lines continue just for the sake of seeing them in the southern hemisphere. So our celestial equator is 90 minus the latitude we're at, which is 21, or the NCP, which is 21. So if I do 90 minus 21, I'm going to get 69 degrees latitude. Or no, I'm sorry, not latitude, where our path would be. So again, it's 90 degrees away. So I kind of like eyeball that and note that it'd be somewhere up here. That might be a little low. Let's go kind of right there. And say that's the celestial equator, 69 degrees. And remember, the CE always goes exactly to the east. Get my hand out of the way. I kind of made that other line so it's in the way there. Okay, so now I need my winter and summer solstice. So remember, I'm below the Tropic of Cancer line. So when you go below it, you end up getting to the point where your sun is going to cross on the north side of the zenith a little bit. My line doesn't look very straight. It's bothering me. Okay, so with that said, I'm going to do the math as I fix this because it was really bugging me. There we go. I'm going to get my winter solstice first. I'm going to take my CE, my celestial equator, which is 69 degrees minus the 23.5 degree tilt. So 69 minus 23.5 is going to be 45.5 degrees. So that means I'm going to go somewhere. If this is halfway is 45, I'm going to be somewhere right in here at halfway. That's going to be my winter solstice at 45.5. And I'm going to parallel, make the lines parallel. I'm going to just draw them down all the way through the southern hemisphere while I'm at it. Okay, so they're parallel to each other, and I need to do my summer solstice, 69 plus 23.5 degrees. So if you do that, you might note that we're going to get above 90. 90 is here. If we're going to get past 90, we're only going to get past 90 by a couple degrees. So I'm going to redraw my zenith so it's not a big X in the way of everything. So we're just going to get barely past it, not much. And again, if we just get barely past it, and I draw it all the way down, okay, we're going to say the summer solstice at 92.5 degrees. Got to put that down there. And I didn't do a perfect job because my lines aren't quite the right spacing. So this might have been a little bit lower, or the CE might have been a little bit higher. I'm not perfect, but it's not awful. I didn't put two super close together and one really far apart, because technically these should be about the same distance apart since they're both 23.5 degrees. But notice when you go beyond 90, you just put it on the other side. Okay, so if I get up to like say 100 and something, I'm just going to keep going on this side. And remember, keep them parallel to the CE. The more we go towards the equator, the more these lines are going to start going upward. Okay, keeping them parallel to each other is key. All right, so that was one that's above the Tropic of Cancer. So, and I'm going to just remind you guys, the tropics equal 23.5 degrees. So the Arctic is the 66.5, the tropics are the 23.5. All right, so I am done with that, and hopefully that will help with your worksheet.